tell me whether you can see the screen or not. Please confirm in the chat box whether you can see the screen, and then I will proceed. Okay, thank you. So now we can proceed. Just give me a few seconds, and here we go. Okay, so now I will show you the whiteboard here. Okay, so let me connect it once. I think it is disconnected. Let me do it once again. Yeah, so now there is some problem in connection. Give me a few seconds. It will be resolved soon. I don't know why it is not connecting. It should connect. Let me refresh it. I don't know why it is not connecting. It should connect. Okay, give me a few seconds. I have to use a different device. Maybe in laptop I have some problem, so I have to use some different device. Okay, let me shift into it. Hello? Hello? Am I audible now?
Yes, sir.
Okay. Okay. Now let me share the screen. Okay, so can you see the whiteboard? Just confirm once whether you can see the whiteboard or not. Okay, okay, now let us start. So, in the previous lecture, we discussed about the stereochemistry part a little bit, and we have seen the symmetry elements present in Allene, right? We have seen the symmetry elements present in Allene, and from there we will start to. So the next topic which we will discuss here is the different projection formulas. Okay, in organic stereochemistry you have to know about the projection formulas in order to write down proper structures and to predict proper reactivity of the molecules. And so the first projection formula, very simple, is the Fisher projection formula. We all know that we represent the Fisher projection formula like this. So here we have carbon atoms skeleton, carbon skeleton like this. This is a simple representation of a molecule. Okay, now what this structure tells us about is, so this is a two-dimensional representation of a three-dimensional molecule, and actually the structure represents that this bond is coming, sorry, this bond is going below this CH3, and also the other CH3, this is also going below, whereas these two, this H, this OH, and this H, this OH, they are coming above. So these four are above the board, above the board, whereas these two, they are below the board, right? Now uh, this is the representation of a Fisher projection formula. So I'm not going into that all the rules of Fisher projection formula, because if you are preparing for CSIR exam, I suppose that you know all these things. But what we have to know here, or what we have to practice here for our target, is how we can convert one projection formula to another, like Fisher to Newman or like that. Okay, so that we will discuss, because that is our point of interest. Okay, so this is Fisher projection formula, and Newman projection formula is, here we represent the front carbon atom by this big circle, and at the other side we have the back carbon atom. Okay, so actually this big circle is the back carbon atom, and in the front carbon atom you can see the carbon atom. So this is our front carbon atom F, and this is back. So here we have some groups, like let's say this is CH3, this is H, and this is OH. On the back carbon we have, let's say, CH3, H, and OH. Okay, this is the thing. This is one molecule. Now here I will discuss another thing. And so this is one molecule, this is, let's say, molecule A, and another molecule is this one, H, OH, OH, CH3, and this is, let's say, CH3, this is H, this is OH. So this is molecule B. Now I have one question for you. Now I'm using headphone here, so you can answer and I can hear you. So just tell me which one is threo and which one is erythro. First, tell me whether you know the threo erythro nomenclature. You know about that? Either you can tell or you can write in the chat box. Okay, so someone have written that second one is the erythro. Okay, so you forgot threo-erythro nomenclature, or I mean, should I have to discuss about threo-erythro? Okay, so you forgot. I will discuss. Okay. So first, someone said the second one is erythro, and let us see whether he's correct or not. So he is telling that this B is erythro. Now, if I tell you, actually you are not correct. B is threo and A is erythro. Now in Newman projection formula, it is very easy, straightforward to classify erythro and threo. So let us see. So this is a specific example, but we can take some general example. Okay, so the general example will be like this. So let's say this is our molecule. Here we have three group. One is large, one is medium, one is small. Okay, and on the back carbon again we have three groups. We have large, we have medium, we have small. So this is one representation. Another representation would be uh, let's say we have the front carbon, same configuration, but in the back carbon the two groups, this medium and small, they will change their position. So here we have medium, here we have small. So let's say this is P and this is Q. Now how we can classify them as threo or erythro? So it is very easy. For threo molecule, a molecule we call threo when all the similar groups are having similar relationship or same relationship. Okay, in the Newman projection formula, if all the similar groups have same relationship, then it is called erythro. Now what is mean by same relationship? So in molecule P you can see that the large group on the front carbon atom and the large group on the back carbon atom both are anti to one another, right? This L they are anti. Similarly, these medium groups they are also anti, and the small groups they are also anti to each other, right? And that's why it will be erythro, right? Similarly, let's say we have a different conformation of the molecule where let's say we have this large, we have this medium, we have this small, and now we have this large, we have this medium, we have this small. So again you can see, although the relationship now is not uh, anti, but this large they are gauche, this medium they are gauche, and this small they are gauche. So relationship remains same, although it is not anti, it is it is gauche, but uh, gauche among all the three pairs, right? And that's why this is also erythro. But if you look at Q, in Q conformation, in Q molecule are not, so these two are actually two different conformations of the same molecule, this one and this one. But erythro and threo, they are not conformation, but they are different configuration, right? They are two different molecules. So in Q, you can see, although these these two groups are anti to each other, but these medium groups, they are gauche to one another. Similarly, these small groups, they are gauche to one another. And that's why it is called threo. So can you understand erythro and what is threo? Write down in the chat box whether you understood or I have to explain it again. Okay, so you understood. Now tell me, between A and B, which one is erythro and which one is threo?
Erythro and B is threo.
Yeah, so A is erythro and B is threo. All right. So you will see that this threo erythro nomenclature, this classification, it will help us to interconvert between one structure to another. How it will help us, we will see shortly. Now, this is about the Newman projection formula. Let us draw the same molecule in the. So first we write it erythro. Okay, so this is erythro. Now we will convert this projection formula to, let's say, flying wedge projection formula. Okay, so what is flying wedge? Flying wedge is actually, this is how we represent a flying wedge projection formula. Uh, which is the general representation. So what here we are doing, we are putting this skeleton in the plane of the board, and this is above the board, this is below the board. Similarly, this is above the board, this is below the board, right? Now you have to look into this molecule, this particular molecule, either from this side. So here your eye should be either here, or you can see it from this side. Okay, so either you can look into the molecule from your left hand side or from your right hand side, right? Now um, because we have drawn the molecule in this way, or let me draw it now. Okay, so first decide whether we will look into the molecule in the from the left hand side or from the right hand side. Now I am choosing from the right hand side, so I am looking the molecule here. So concentrate your mind and look into the molecule from here. Okay, so if I look into the molecule from here, I will first draw a line, and this line represents the bond between the front carbon atom and the back carbon atom, right? The front carbon atom and the back carbon atom. Now you can see, if I look into the molecule from here, on my right hand side, I will have the CH3 group at this position, this CH3 group. So if I am looking from here, I will see that on my right hand carbon atom I have this CH3 group. So I am writing this CH3 group over here, and now one bond will come above, another will go below. Similarly, on my left hand side, I will have a CH3 group at the bottom side. So I have this CH3 group, and here I have one bond above, another bond below, right? Now again you can see, as I am looking from here, so this OH group at my right hand side is near to me, right? So it is near to me, that means it is above the plane. Okay, so here I will put the OH group, and automatically the hydrogen will go below. Similarly, uh, if I look into the left carbon atom, you can see this hydrogen atom is towards me. or it is near to me, so that means it will go above and automatically the OH will go below. So this is how, looking into the molecule in the Newman projection formula, we can easily convert it to the flying wedge projection formula. Okay, and it is very handy when you will solve problems of Felkinen model or other related other related stereochemical models. Then final answer you have to give in the either in the flying wedge projection formula or in the Schauer's projection formula, but you have to do the exercise in the Newman projection formula. So this interconversion is very important. Now we can verify whether this drawing is right or not by looking into whether it is threo or erythro, and the rule is same here also. The relationship of the among the groups will be similar because it is erythro. In the beginning we had erythro, so this will also be erythro. And now you can see this methyl they are anti to one another, this OH they are anti to one another. Similarly, this hydrogen they are anti to one another, and that means this is erythro. In the other way we can say that, what we can say, so I just erase all these things. You don't have to put your eyes here or there, you just draw a line. So you just look at your right hand side once and you put the CH3 above, then you put the other CH3 below by looking at the left hand side, and then just look whether your OH is below, OH at the right hand side is below or above. So it is above, so you put it here. So you don't have to look into the molecule again because you know it is erythro, and by only one way you can do it erythro is you have to put uh, hydrogen here, and in this carbon atom you don't have to look into the molecule, you know it is erythro. So that means you have to make this OH group anti to one another, so you have to put the OH group here and hydrogen group here, right? So this is how, by looking at or by determining whether your structure is threo or erythro, you can easily interconvert between one projection formula to another. This is very handy. I don't know whether it is written in any books or not, but I uh, personally use this trick while inter converting one structure from another, and I never do any mistake. So I will also suggest you to do the same to avoid any mistake. Okay, so tell me whether you understood the process or not. Just confirm once whether you understood the process or not. Then I will proceed. You can write in the chat box or you can also tell. I can hear you. Okay. Okay, so you understood. Now let us go into our next topic, and that is about chirality. So again, I will not talk much about chirality. You all know that a molecule will be chiral when there is no um, symmetry of second order, or that means if a molecule you have S like Sn, S1, like S2, S3 or anything Sn, or if you have any sigma plane, then the molecule will be achiral. If these two are not present, then the molecule is chiral. Only if only let's say Cn is present, then the molecule will be chiral. So the condition for chirality is very simple. Your molecule shouldn't have any symmetry of second kind, that is Sn or sigma. Now there is a definition for this, and the molecules which does not have these two symmetry, they have a different name. Okay, they have a different name, and we call it asymmetric and disymmetric. So what is asymmetric and what is, let's say you have a molecule which only has some CN axis. Okay, can you give example of a molecule which has CN axis where N is greater than 1, that is not C1, because C1 is present in every molecule. So you have a molecule which has Cn, it may be C2 or C3, anything, but it doesn't have any other symmetry like sigma or Sn, nothing. Can you give example of one such molecule? Just think and give give an example. HCl. But in HCl you have plane of symmetry, right? The molecular plane is itself a symmetry plane.
Sir, NH2, NH2.
NH2. NH2, NH2. I mean hydrazine.
Yes, sir.
Hydrazine you are talking about?
Yes, sir.
Okay, so hydrazine, the configuration will be, no, hydrazine, it has sigma, right? All the groups are same, so it has sigma. What about Allene? Let's say you have this Allene where, so normally in Allene we have sigma, right? In normal Allene where all the groups are same. But let's say you have this Allene where you have hydrogen here and Cl here and hydrogen here and Cl here. Okay. Now, what are the symmetry elements present in this Allene? Can you tell what are the symmetry elements present in this Allene? This C2 is absent, right? This C2 is absent or it is present? Yeah, so someone have wrote down C2. So which C2 you are talking about? This C2? This C2 you are
Perpendicular
talking.
C2.
Yeah, so this C2 is present. Now, whether any sigma is present in this molecule? There is no sigma, right?
Yes, sir.
Okay. So there is no sigma. So this is an example of a molecule where you have C2, where Cn n is greater than 1 and there is no sigma, no Sn, right? And that's why this molecule is called asymmetric molecule. Asymmetric molecule. Now these asymmetric molecules, they are chiral. All asymmetric molecules are chiral. Okay, so the condition for chirality is the molecule should be asymmetric. Now what is disymmetric? Now you can have other molecules where you don't have C2, C3, anything. You don't have sigma, you don't have Sn, you only have C1. Let's say you have a simple chiral molecule where all the groups are different, like this. Let's say you have hydrogen, deuterium, fluorine, and chlorine. Okay, this is a molecule where you have only C1. There is no Cn where n is greater than 1. There is no sigma. There is no Sn, right? This kind of molecules. And they are called disymmetric. Okay, these molecules are called disymmetric. I think I just shuffled between these two. The previous one should be desymmetric, and this one is actually asymmetric. Okay, so this one is asymmetric and previous one will be desymmetric. So if a molecule contains only C1, that is called asymmetric, and if a molecule contains Cn, where n is greater than 1 but nothing else, then it is called desymmetric. And both these molecules, asymmetric and desymmetric, they are chiral. So the condition for chirality is, in order to be chiral, a molecule should be desymmetric, molecule should be asymmetric or at least desymmetric, right? Both are fine. If it is asymmetric, then it is chiral for always. But if it is not asymmetric, if it is desymmetric, then also it is chiral. Okay, so we can say that this S and this sigma, they are the symmetry elements which destroys chirality within a molecule, and if these chirality destroying elements are absent, the molecule is chiral. Now here comes two more things, two more definitions, and these definitions are very important. You should know about this asymmetric, desymmetric, these are interview questions. Okay, the second two definitions are the stereogenicity and chirotopicity. Stereogenicity. First, we'll talk about stereogenicity and then we'll talk about chirotopicity. So, can you tell what is called stereogenic or what is called stereogenicity? Do you know that? Stereogenicity. If you don't know, that is completely fine, but tell me whether you know or not. What is stereogenicity? You know that? What is called a stereogenic center? Okay, so no one is answering.
4 different group.
Yes, tell.
Stereogenic center means a chiral center. Means 4 different atom or group attached.
Yeah, so
So
so the
application,
yeah, so what you are telling is completely correct, but the definition is if within a molecule you exchange between a pair of ligands, and on doing so, if the configuration of the molecule is changed, then the center is called stereogenic center. Okay, and this phenomenon is called stereogenicity. Let me show it you by one example, and I will use the similar example which I have just drawn. So you have this molecule. Let's say you have chlorine, bromine, deuterium, and hydrogen. So this is one molecule. Now, if you exchange between this pair, this hydrogen and deuterium, you will get this molecule, right? And these two are different, right? These two are different. So by exchanging two ligands, mutual exchange, we are changing the configuration. So if we do the configuration, so this one is, this is A, this is B, this is C, this is D, and now this is A, B, C. So this is moving clockwise, but hydrogen is towards us. It is clockwise, and that means the configuration will be S, right? The configuration will be S, and for this one, the configuration will be for sure R. Okay, so by exchanging two ligands, we are changing the configuration of the center from S to R, and that's why this center is called stereogenic center. So here the main thing is, by exchanging ligands, you have to exchange the configuration, or you have to change the configuration of the molecule. Now, what about chirotopicity? The next thing, chirotopicity? Can you tell what is chirotopicity? Can anyone tell what is chirotopic or what is chirotopicity? This is more simple. So if you have a chiral molecule, let's say this one, chlorine, and let's say this is iodine. So this is a chiral molecule. All the groups are different. There is no sigma, there is no SN. So this is chiral molecule. So if you have a chiral molecule, and then all the centers within the molecule will be chirotopic. So let's say you have a different center. Let's say you have a methyl group. So this methyl group, this center, all these 5 centers in the molecule, all the centers are chirotopic. Okay, so here the condition is simple. The molecule should be chiral. The molecule has to be chiral, and then all the centers within the molecule will be chirotopic, and this is called chirotopicity. Now, the interesting thing is, so let me ask you, what do you think? Can a molecule be chirotopic and still it is non-stereogenic? Is it possible? Because what we have seen here is, this is an example of chirotopic molecule or chirotopicity, like this hydrogen, deuterium, CH3 and iodine, and here if you exchange between 2 ligands, the configuration will generally, we can see that if a molecule is chirotopic, then it will also be stereogenic. But what do you think? Is it possible? Yeah, so someone said it is possible that a molecule can be chirotopic and still it is not stereogenic. Okay, so it is possible. And what about the vice versa? That is it possible that a molecule is stereogenic but it is not chirotopic? Is it possible? And can you give some examples of such kind of molecules? Okay, let me give you one example. Let's say this is our molecule. Okay, here we have OH, OH, OH. Here we have hydrogen, 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 and another molecule. Not another molecule, just we are drawing it. Okay, so first let me tell you that this molecule, so you tell me this molecule whether it is stereogenic or not. Is this molecule stereogenic? So I just have given the definition and example of stereogenic molecule and stereogenicity. So based on that, can you tell it is okay? So Ajay is telling it is, yeah. So you are telling S. I am not asking about configuration, but I am asking about whether this molecule A is stereogenic or not. Someone said it is
Sir,
not stereogenic. So
the
yeah, tell
stereogenic.
me.
If we change interchange H and OH, carbon first carbon, then we got the chiral center active molecule. So it is stereogenic.
Tell again.
So if we change carbon number 1 ligands, H and OH interchange, and
This carbon,
then carbon, yeah,
you are talking.
yes,
Okay,
yes.
okay. Let me change it. So it is H OH, and now this is OH H OH H. Okay. This is what you are talking about. So first tell me, what is the configuration of this center? R or S? So it is S, you are telling this is S. Now if this is S, what will be the configuration of this one?
This one also be S.
S. Everyone agree with that? So there is a trick. You don't have to do A, B, C, all these things. If you just find out configuration of one center, let's say we want to find out the configuration of this one, and someone said this is A. So let us check whether it is correct or wrong. So this is A. What will be B? This one or this one? Which one will be B? This one will be B, right? And this is C. So A, B, C, it is moving anti-clockwise. It is moving anti-clockwise, and in Fisher projection formula, anti-clockwise means
S.
anti-clockwise
H
means
is
what?
A. So anti-clockwise means S.
But it is in
What?
Fisher projection formula, right?
Yeah.
So in Fisher projection formula, anti-clockwise means S or R.
S. But hydrogen is horizontal, so the
Yeah.
configuration will be changed.
Yeah. So no, it is not S, right? So we just remember that if the ABC clockwise it is R, and if ABC anti-clockwise it is S. But it is true when the fourth atom, that is the group which has the least priority, that is below the plane, right? When the hydrogen is below the plane, right? Am I telling right?
Yes, sir.
This clockwise R and anti-clockwise is this rule is applicable when your least prior group is at the bottom or at the rear side from you. But in Fisher projection formula, this hydrogen is pointing towards you, right? So it is above the plane. It is above the plane. So the rule will be reverse. So here clockwise means S, anti-clockwise means R, right?
Okay, sir.
Yeah, so that means it is not S, but it is R. So it will be R. Now, if this is R, and if you place a mirror over here, so you can see this part is actually mirror of this part.
Okay.
Is it so?
Yes, sir.
So you don't need to find out the configuration of this center. If this is R and if this part is mirror of this, so what is the mirror of R?
R.
Mirror of
What?
R is S.
Yeah, so mirror of R is S, so this will be automatically S, right? So now this is our R, this is our S. And then if we change the position of these two, so it will stay S, but this will now also become S as we change this OH and this hydrogen, as we do the mutual exchange, right? So what you have said is completely correct, that when we are changing the exchanging between two ligands, the configuration is changing, and this is the reason this molecule is stereogenic. But you said that by doing so we are making chiral or something. In stereogenicity, in the definition of stereogenicity, there is no mention of chiral word. There is no chiral word. So when you are asked whether a molecule is stereogenic or not, you don't need to see whether the molecule is chiral or not. Chirality is nothing to do with the stereogenicity. Keep this thing in your mind. Okay, when we are talking about stereogenicity or stereogenic center, there is no relation of it with chirality. A molecule can be stereogenic, at the same time it may not be chiral, and this molecule is an example of that. So we have seen that this is stereogenic, but now tell me whether the molecule is chiral or not. What do you think? This molecule A and molecule B, both these two, they are chiral or not?
Molecule A is achiral because there is a sigma plane carbon
Yeah,
number 2, or molecule B is chiral, there is no sigma plane.
are you sure?
So sorry, B is also achiral. There is also is
No, you are correct,
sorry.
right? B is chiral. I am just
Yeah.
asking. B is chiral. There is no symmetry plane. There is no symmetry plane here, okay? Because here you have hydrogen, here you have OH. So these two
Yes,
are
yes.
not, but in A you have a plane of symmetry. So that means in molecule A there is a plane of symmetry, and this plane of symmetry is destroying the chirality of the molecule. So this molecule is not chiral. So if the molecule is not chiral, then it will all the centers in the molecule will be achirotopic, right? So this is an example where a molecule is stereogenic but not chirotopic. Understood?
Yes, sir.
Okay. Then we will see and one thing forgot to mention is the center which is actually destroying the chirality, the center through which the plane of symmetry is passing, that center is called pseudo asymmetric center. Okay, there is a name. Now we will see an example. Let's say this is our example. C double OH, C double OH, and here we have this OH, H, H, OH, H, OH. Okay, this is our molecule. So this is actually the previous molecule when we exchange the ligands, and here you will see that this is the configuration R, and this is also R. Now tell me, uh, first tell me whether the molecule is stereogenic or not, and then tell me whether it is chirotopic or not. First tell me whether it is stereogenic.
Yes, stereogenic and also chirotopic.
Mm, so how it is stereogenic?
So if we change interchange H and OH carbon number 1, then R will be S.
This carbon. Okay.
Carbon
So
number, okay,
so
R.
so actually telling a molecule as a whole is stereogenic is actually not correct, because a particular center is stereogenic or non-stereogenic, but as a whole the molecule is not stereogenic. I mean, the stereogenicity definition is not for the molecule but for a particular center. So this particular center is stereogenic, and you are correct. But what about this center? The carbon number 3. What about carbon number 3? Whether this center is stereogenic or not?
This center
This
is
center,
not
this particular.
stereogenic because
Why?
if we because the two ligand which are attached is same, so we cannot
Hmm.
distinguish.
Yeah, so you cannot give a nomenclature for the center R or S, right? So
Yes, sir.
to give a nomenclature, you need to have two different groups. One should be R and another should be S. Then only you can decide the priority and you can do the nomenclature. But if two groups are R, then you cannot do the nomenclature. So if you cannot give a name, then how the name will be changed when you will exchange the ligand? So that means basically if you change the two ligands, so what you will get? So if you change also uh, if you change the ligands, this center you cannot distinguish, right? You cannot give it R or S nomenclature, and that's why the definition that on doing mutual exchange the nomenclature should be changed or the configuration should be changed, that is not applicable here, and that's why this center is not stereogenic. But uh, because there is no pseudo asymmetric center, there is no plane of symmetry, the molecule is chiral, and that's why all the centers including this center is chirotopic, right? So these two examples are very important. These are favorite questions for interviewers. They will ask you give some example where the center is stereogenic but not chirotopic, and give a molecule where centers are chirotopic but not stereogenic. So then you have to give these two examples. So these two are very important examples. Now let us move on to our next topic, that is the nomenclature. Now I will not discuss about the nomenclature of simple molecules, because you all know that simple molecules, simple chiral centers. But still, let me discuss few examples. Okay, so yeah, so first example will be this one. Quickly give me the answer. What is the configuration of this center, this star? What is the configuration? Quickly tell.
R.
Everyone agrees with that, or we have some different opinion? Okay, so you are correct. It is R. Now let us see the nomenclature of Allene system, Allene and biphenyl system, because that is our point of interest. Okay, so we'll uh, look into Allene and biphenyl, because that's what will come in the exam. So Allene system is represented like this. This is simple example, and so how we have to do the nomenclature? So we have to look into the molecule either from this side or from this side, right? Let's say we look into the molecule from our right hand side. So then our near, so here the zeroth rule of CIP nomenclature comes, that is near end precedes far end. There is a zeroth rule of CIP. So this is our near end. Okay, and this will precede the far end. So we represent it by a thicker line, and on our right hand side we have Cl, on our left hand side we have hydrogen, on top we have hydrogen, and on bottom we have chlorine. Now priority will be given this chlorine, because both hydrogen and chlorine are at the near end. So the atom with higher molecular weight will get priority, so it will be A, this will be B. For the same reason, this will be C and this will be D. And here there is no such thing like whether it is away from us or towards us. Always clockwise means R, anti-clockwise means S. So now this A, B, C, this is what? This is anti-clockwise and this is S. So this is very simple for Allene. Now let us see the process for biphenyl, and for biphenyl system it is actually similar. So this is an example of biphenyl system. This is an example of biphenyl system, and here let's say we have hydrogen, here we have iodine, here let's say we have chlorine, here we have methyl. Okay, now again we can either see the molecule from this side or we can see the molecule from this side. Now this time we will look into the molecule from the left hand side. If we look into the molecule from the left hand side, these two are our near atoms, so we put it horizontally. Okay, and now here we have hydrogen, here we have iodine. On our right hand side we will have methyl, on our left hand side we will have chlorine. So this iodine will get the priorities, which is A, this is B, and now this is C, this is D. Now many people mistake that, they think that because it is hydrogen it will be it will have the least priority. You don't have to mess between the normal chiral center and an Allene or biphenyl system. In normal chiral center, the priority is decided only based on the atomic number or the highest isotope, like that. But in case of Allene or biphenyl system, you have to decide which one is far end and which one is near end, and based on that you have to give the priority. So this is our priority order, and here this A, B, C is moving again anti-clockwise. So we don't have to see whether hydrogen is towards us or whether it is away from us. We don't need to see that. We just have to see whether it is anti-clockwise or clockwise, and because it is anti-clockwise, so again it is S configuration. So this is very simple, right? Do you have any difficulty in understanding this nomenclature of Allene and biphenyl? If you have any difficulty, you can ask. Everyone understood?
Yes, sir.
Yes, sir. Once a time.
Once more? Okay, once more. Okay, so someone said once more, so I will repeat it. So this time I will repeat, and this time I will look into the molecule from the right hand side. Okay, so let us suppose that we are watching the molecule from the right hand side. So if you watch the molecule from the right hand side, then these two groups, this chlorine and this methyl, they will be your near groups or near end. So we just put a thick line like this. Okay, now we we are looking at the molecule from here. So in our right hand side we have chlorine, so we put chlorine in our right hand side. In our left hand side we have methyl, so we put methyl over here. And on the rear side we have hydrogen. It is at the top side, so hydrogen is at the top, and this iodine is at the bottom, so iodine is at the bottom. Now always the priority should be given to the atoms which are at the near end. So although this iodine is having the highest atomic weight among all these four groups, but this chlorine will get the first priority because it is at the near end. So this chlorine is A, the methyl is B, then iodine is C, and hydrogen is D. And now this A, B, C, you can see it is anti-clockwise, so that's why it is S. So Ajay, is it clear? Is it clear now?
Yes, sir. Yes, sir. Yes, sir.
Okay. Okay. So these Allene biphenyl systems, they generally come in your exam, the nomenclature. Now another thing is, let's say you have given this molecule. Cl, Br, iodine, H. Okay. So what do you think? The whether the molecule is chiral or not?
Chiral,
What
sir.
about? Okay, someone said chiral. What about this one? What about this one? So this is A, this is B. Whether both are chiral and or uh, which one is chiral and which one is achiral? Okay, so Avinasha is saying that no, but what is no? I mean, yeah, B is chiral. So someone is saying B is chiral and A is achiral. Okay, so here one thing you have to remember. What? That is, if you have, so here the carbon numbers are 1, 2, 3, 4. Here it is 1, 2, 3, 4, 5. So if you have even number of carbons, then the system is planar. If you have odd number of carbons, then the system is not planar. So that you can just remember by remembering simple ethylene molecule and Allene system. So in ethylene molecule, you have two carbons. That is even system, and that is planar. That is not chiral. But in Allene, you have odd number of carbon atoms, and that one is non-planar. That one is chiral. So this is a confusing question. I myself did mistake in one exam. I didn't look into the molecule carefully. They just given the molecule as if it is a Allene system, but you have to count the number of carbon atoms present in the molecule. If it is even, then it will be achiral. If it is odd, it will be chiral. So this is a very important question. Okay, both are achiral. No, both are not achiral. The second one, because it has 5 carbon atoms, so if you look into the overlap of the orbitals, you will see that whenever you have odd number of carbon atoms, the two ends will be non-planar and they will be chiral. But again, maybe in some cases they will give you odd number of carbon atoms, but the groups will be same. Then there will be a plane of symmetry and the molecule will be achiral. For example, let's say you have given this one, Cl iodine, but here let's say you have both deuterium and deuterium. Now, in this case, although these two groups are different, but there is a plane of symmetry which is bisecting this center. So, the symmetry plane is containing this iodine and this chlorine, and it is bisecting these two deuterium atoms. Okay, so although you have odd number of carbon atoms, but because the groups are oriented in such a way that it is not chiral. So when answering these questions of chirality, you have to look into all these factors, whether all the groups present are different or not, whether the system is planar or not. All these things you have to look into, and then you have to carefully answer. Then there is a minimal chance of mistake. Yeah, so this is the thing. And so these are the preliminary things which you have to know in order to study the organic stereochemistry. These are actually revision things. And in our next lecture of stereochemistry, we will actually discuss about the cyclic systems, the cyclohexane system. So actually we can start some of that in this lecture, the cyclic systems. Okay, so cyclohexane is a very important system in organic chemistry, and based on this system you will be asked many questions. Now I will not talk about the flipping and all these things of cyclohexane system. You know that cyclohexane flipping can occur in two ways, or if you tell, I will discuss. Explain the nomenclature in, okay, adamantum. Okay, so in adamantum system, uh, yeah, so this is an important thing. Thank you for remembering. But to discuss about adamantum, I have to search about examples first, and then I will present that examples. Today I am not ready with that, so maybe in the next lecture I will find out the examples, important examples, and I will discuss it. So thank you for remembering. I will note it, and in the next lecture I will show the examples of adamantum. Yeah, it is important topic. Okay, now we are talking about cyclohexane system, and so cyclohexane flipping can occur, and this flipping can have various consequences on the reactivity of the molecule as well as the stability of different conformations. Okay, and today in this short part, so this lecture I will end just after 5 or 10 minutes. So in this 5 or 10 minutes I want to discuss about one important thing, and that is anomeric effect. So in case of cyclohexane system, anomeric effect is very important. But before that, we want to discuss about the negative hyperconjugation which exists in the acyclic system also. Okay, so tell me, what will be the most stable configuration of 1,2-difluoroethane? This is anti, and this one is gauche. So which one will be more stable? Gauche is more stable, someone said. But what about when we change the fluorine to chlorine?
If we
Then
change
which one?
chlorine, then anti conformation will be more stable.
Sorry, here I just did a mistake. Yeah, so when we change it from fluorine to chlorine, the anti is more stable. Now, can you explain why in case of chlorine the anti is more stable, and in case of fluorine gauche is more stable?
Uh, because in case of fluorine is more electronegative than chlorine, and there is a effective hydrogen bonding occur. In case of chlorine, it's larger in size, and so to minimize repulsion, and anti-conformation will be most favorable.
Yeah, for chlorine it is and coulombic repulsion, but in fluorine, what you have said, hydrogen bond.
Yes, there is a interaction between chlorine and hydrogen.
How? I mean,
Uh,
which hydrogen and which fluorine? Can you tell?
uh, uh, If we the axial hydrogen
Okay,
front
so
carbon,
okay, so I will give number. So let's say yeah. So I don't need to give number, but this is, let's say this is anti hydrogen, and this is gauche hydrogen, right? So and so which hydrogen will interact with the fluorine? Anti hydrogen, or we are talking about this fluorine? So which hydrogen will interact? Gauche hydrogen or anti hydrogen?
goes hydrogen.
This hydrogen, this one will interact with this one.
Yes,
These
sir.
two will interact. How?
But this configuration is not stable because there is a two fluorine atom. Uh,
No, you have said that gauche is more stable. So
yeah,
this one is gauche,
goes
right?
goes is more stable. Uh,
Huh.
so
So what is the source of this stability? So someone said in the chat box it is negative hyperconjugation. So have you heard about negative hyperconjugation? So normally what is hyperconjugation? In case of hyperconjugation, we have a positive center and we have a adjacent CH bond, and that CH bond donates electron towards the positive center, right? This is hyperconjugation. Then what will be negative hyperconjugation? In case of negative hyperconjugation, what will happen? In case of negative hyperconjugation, is it negative hyperconjugation or it is hyperconjugation only? Okay, so let me tell you. So if you look into the molecule carefully, I just, let me draw it once again, the Gauche conformation. So one thing is clear, that the Gauche form is more stable. Now let me draw the Gauche form once again. So uh, okay, so yeah, let me do it in another way. Fluorine, hydrogen, hydrogen, and in the back carbon we have fluorine, hydrogen, hydrogen. So this is Gauche form. Okay, now if you look carefully, if we focus on the CF bond, this CF bond, we have this CF sigma star, right? We have this CF sigma star. Okay, and also we have this CH sigma. Okay, so this CF sigma star and this CH sigma, they are parallel to one another. You can see they are parallel to one another. We can show it by the flying wedge projection formula also. So let's say this is our one fluorine atom, this is our hydrogen atom, and because we are talking about the Gauche form, so our another fluorine atom will be here. Here we'll have hydrogen atom, we'll have hydrogen atom. Now we are talking about the CF sigma star. So here we have the CF sigma star. So this is our CF sigma star, and here we have this CH sigma. CH sigma, and you can see this orbital, this CH sigma orbital and this CF sigma star orbital, they are parallel. This one is filled, this one is filled with electron, and this one is vacant, this one is devoid of electron. So they can overlap like this. These two are parallel, so they can overlap. They can have overlap. We can represent it by this way. This hydrogen, this is fluorine. We can represent it like this: F minus H plus. Similarly, like hyperconjugation, right? So there is a double bond kind of thing. Similarly, this CF bond can also interact with this CH bond. So two such interactions are possible, the CH sigma and the CF sigma star. But if you talk about the anti conformation of the molecule, where the fluorines are anti to one another, sorry, fluorines are anti to one another, there is no such sigma to sigma star interaction, because on in this case the CF sigma is actually parallel to the CF sigma star, and CF sigma cannot donate electron. This bond is very strong, but CH sigma can donate. So the hyperconjugation or this sigma to sigma star donation, actually we should say it sigmas to sigma star. It is not purely hyperconjugation, but it is sigmas to sigma star donation. This sigma to sigma star donation is not possible for the Gauche, the anti-conformation, but it is possible for the Gauche conformation, and that's why the Gauche form is more stable. Now, if we talk about the chloro compound, the 1,2-dichloro compound, then some sort of this interaction is present there, but it is less, because at that situation, the sigma star, the Cl sigma star, if we consider this sigma star, the energy of this sigma star is relatively higher. Okay, the energy of this sigma star is relatively higher. The energy of this CF sigma star is relatively lower, and in order to have a proper overlap, the orbitals should be in similar energy. So the CH sigma bond, this CH sigma bond, they can interact with only those orbitals, those LUMO, which are in similar energy or at the same level with this sigma bond. And because fluorine is very highly electronegative, so it brings down the energy of the sigma star and it becomes close to this sigma, CH sigma, so they can easily overlap. But in case of CCl bond, the sigma star is of high energy and they cannot overlap. So the amount of this sigma sigma star interaction present in dichloro system is very negligible. We don't need to consider it. At the same time, chlorine has bigger size, so there is a tremendous amount of steric as well as coulombic repulsion, and this makes the anti conformation more stable. So this is called Gauche effect. This sigma to sigma star stabilization, this is called Gauche effect, and this Gauche effect is only present in case of fluoro compound, not for the chloro compound. Now the similar kind of effect is seen in case of cyclohexane system also, and that is called anomeric effect. Okay, so it is actually present in case of carbohydrate system, but any cyclohexane system where you have a electronegative atom like oxygen over here and some other electronegative atom, mostly halogen over here, let's say chlorine. So if this chlorine is present in the in the axial position. So in case of cyclohexane system, you have two position. This is equatorial position, this is axial position. If it is in axial position, there is some extra stability. So if you compare between these two, so the flipped structure would be this one, where the chlorine, uh, this is chlorine and this is hydrogen. So here the chlorine is equatorial, hydrogen is axial. Okay. Normally if you consider two cyclohexane systems like these two, let's say you have oxygen, same system, let's say you have methyl and its flip structure, sorry, I just have to make it similar. Methyl and this one methyl over here. Okay, so this is oxygen, this is oxygen. Okay, so if you compare A and B, which one is more stable? Between A and B, which one is more stable? Can you tell? Very easy, right? Okay, so B is more stable. The reason is, in case of A, you have these hydrogen atoms in the axial group. So I just have to erase it. So here you have two hydrogen atoms in the axial position. So here you have one hydrogen, here you have another hydrogen, and these two hydrogen actually interact with the methyl group. So here you have this methyl hydrogens. Yeah, so they will interact sterically. There is a steric hindrance which is not present here because it is now now in the equatorial position. This is also called Gauche butane interaction. Anything you can call either axial interaction or Gauche butane interaction. Both are actually same. So because of this Gauche butane or axial interaction, B is more stable while methyl is in the equatorial position. But what about this? If this is P and this is Q, so in case of P, the oxygen is in the axial position. In case of Q, in case of P, the chlorine is in axial position. In case of Q, the chlorine is in equatorial position. In this case, which one is more stable? P or Q?
P is more
Which one
stable.
is more stable?
P,
P is
P,
more stable. Why? Why?
P. Uh, because the anomeric effect.
Yeah. So anomeric effect. What is anomeric effect? Which orbitals are involved? So
So,
if you look, yeah, tell.
so
Yes, tell.
the lone pair of the oxygen atom
Yes.
and
So lone pair of oxygen means the non-bonding orbital on oxygen atom.
yes,
So two
yes,
lone pairs are
and
present. These are non-bonding orbital and
the sigma star of CCl bond.
yeah. So
CCl bond.
this, yes, this sigma star. So this non-bonding pair is actually parallel to this CCl sigma star, and it can donate electron over here, right? So we can represent it like this. O double bond Cl minus plus, right? So this is called anomeric effect, and due to this anomeric effect, this P is more stable. This anomeric effect is not possible here because if we draw the orbitals, you will see that here if we draw the orbitals, you can see the orbitals are not parallel. So here the oxygen orbitals will be, one will be this and another will be this. So neither this one nor this one are parallel to this sigma star, and that's why the electron donation is not possible here. So this is the reason Q is less stable compared to P. So P is more stable, right? and you will see that a lot of molecules are there which are actually stable due to anomeric effect, and if anomeric effect would be absent, the molecule would not be stable, and we will discuss such examples in the next lecture. So actually these lectures, this is our lecture 3 or 4, and up to lecture 5 6 we will discuss about these preliminary things. Then we will go into the actual syllabus of the csir-net exam, that is which will come in the exam. This will also come in the exam, anomeric effect and all these things, but till now we are talking about very basic things. So we are developing our course, and as we proceed we will go into the deep of the course, and we will discuss about more interesting and more important examples. So that's for today's video, and thank you for attending the lecture. Our next lecture is on the next week, so thank you everyone. uh, Interconversion, which interconversion, Ajay? Which interconversion are you talking about? Okay, Newman to Schwarz. Okay, let me do it once again for you. Uh, Newman to Fisher, or which one? Fisher to what? Among all these three? Okay, let me do it. Okay, so let us take an example. Let's say this is CH3, this is CH3, this is a molecule. Let's say OH, H, here we have H, OH. Okay, so this is Fisher projection formula of a molecule. Now, one thing you have to remember is, in Fisher projection formula, the molecule always present in the eclipsed form. Okay, in the Fisher projection formula, the molecule is always present in the eclipsed form. You cannot draw a molecule in the staggered form in the Fisher projection formula because it is by default eclipsed. But we draw the molecules in Schwarz or Newman projection formula, or in flying west formula. All we draw in, generally we draw in the staggered form, but we can draw in the eclipsed form also. So first we will draw the same molecule in the Newman projection formula, but in the eclipsed form. You just randomly draw a Newman projection formula, but what you have to do is you have to do it in the eclipsed form. Okay, now you can look into this molecule either from this side or from the top side. Okay, and because I have drawn this in this way, so I have to, okay, so let me erase it. I have to draw it in other way. So let me uh, so let us think that we are watching the molecule from the bottom side. Then we will put the CH3 group over here. Okay, and on our right hand side we will put hydrogen, on our left hand side we will put OH. So this is our CH3, it goes here. This is our hydrogen, it come here, and this is our OH, it goes here. Okay, this is simple. Now what you have to do is you have to put the other group. So we just put over here the things. Okay, now we have to see whether this molecule is in the threo form or in the erythro form. And we can see this methyl, they are anti to one another, but other two groups, their relationship is not anti. So this here you cannot say anti or Gauche because it is Fisher, but for Fisher projection formula to define threo or erythro, we have to see whether same groups are in the same side or the same groups are in the opposite side. So in this case, you can see this methyl, they are in the same side. Both are away from us. But here the hydrogen and the other hydrogen, they are not in the same side. So that means it is threo. The erythro form of the same molecule, actually the erythro form would be something like this: CH3, CH3, OH, OH, hydrogen, hydrogen. This would be erythro form, and this is threo form. So we confirmed that the molecule is threo, and accordingly we have to put the groups over here. Okay, so now in the threo form, you can see this CH3 and this CH3, they both are away from us. That means they are in the same side. So we put other CH3 group over here, and because it is threo, so we put OH over here, hydrogen over here, right? Why we are doing so? Because you can see this OH and this hydrogen, they are in the same side, so we are putting this hydrogen and this OH in the same side. Similarly, this OH and hydrogen in this side. So you just have to draw one carbon atom carefully, and then looking at the molecule, whether it is threo or erythro, you can put the other groups very easily. Now, some people say that because Fischer projection always represent the molecule in the eclipse form, so during interconversion also we have to first put the molecule in the eclipsed form, and then we have to make it staggered by rotating. By rotating, you can do it staggered, but there is no need of that. Why? Because we are classifying as threo or erythro, and if we know it is threo or erythro, we can directly draw the staggered form. How? So I just have to erase these things. So now, instead of doing eclipse form, we just draw the staggered skeleton. So this is staggered skeleton. We put the CH3 group over here, right? Although in the eclipse form, this CH3, they are in the same side, but because we are drawing it in the staggered form, we are putting the CH3 and making them anti to one another. Now, because we are making them anti to one another, and it is threo configuration, that means that two other groups will be Gauche to one another. So we have to put the hydrogen over here and the OH group over here. Okay. So this is how you can directly draw the molecule which was in the eclipsed form. You can directly draw it in the staggered form. And now doing it to the Shawhurst is very simple. How you can do it? Again, you have to look into the molecule from either from the right hand side or from the left hand side. If you look into the molecule from the right hand side, what you will see? So first you draw the line which represent the bond between front carbon atom and the back carbon atom. So this is the line. Now we are looking into the molecule from the right hand side. Now in case of Shawhurst, we generally draw it in a tilted line. So this is a tilted line. Now we are watching the molecule from here. So in our right hand side, we have this CH3. So we put the CH3 over here. Here also we have one CH3. So we put it over here. Now it is very simple. You just have to make it what? You just have to make it threo. So this center, if you look on my right hand side, I have a hydrogen atom which is towards me, right? This hydrogen atom is towards me. So I put the hydrogen atom here and the OH atom here. Now because it is threo, so I have to make the group Gauche. So that means I have to put the hydrogen here and the OH here. So this is how you can easily make it in the Shawhurst form, or you can directly draw Shawhurst form from the Fischer. So you can directly draw it in the Shawhurst form. So you just look into the Fischer projection formula. You draw a line like this. You put methyl group over here, So I will first try it in the eclipse form. I put one methyl over here, other methyl over here. Okay, so now you can see this methyl group is this methyl group, and this methyl group is this methyl group. Okay, so two other groups will be like this, right? Now you have to look into the molecule very carefully. So these two groups are actually, all these four groups, they are directing towards us, right? In this particular representation, they are directing towards us, but what we are drawing here is it is going downside, right? And now you have to decide from where you are looking at the molecule. So actually we are looking at the molecule from the back side, right? We are looking at the molecule from the back side. Now let's say this is our carbon 1 and this is our carbon 2. So we make it carbon 1, this is our carbon 2. Okay, now tell me, if this is our carbon 1, which one will be hydrogen and which one will be OH? So if this is our carbon 1, you can see, if we look from the back side, what we will see? We will see on our right hand side we have hydrogen. So here we have hydrogen, and on our left hand side we will have OH. Now we just have to make it threo. So what we have to do, because these methyl groups are in the same side, they will not be in the same side. So we have to put OH over here and hydrogen over here. So this is how you can make it in the Shorts. Understood, Ajay? Okay, okay, okay. So I will stop the lecture here, and in the next lecture we will continue from this portion.
हेलो हेलो सर
Yes,
हेलो सर वो
yes,
आपने वो बताया
Gautam.
फ्लोरीन फ्लोरीन वाला बताया था ना सर वो आपने सॉहाश टैगल वाला
Hmm.
वो
Hmm.
गौचे वाला एंटी वाला उसमें रीजन सर
Hmm.
आपने एंटी बॉन्डिंग बताया था ना एंटी बॉन्डिंग बताया था ना उसमें रीजन फ्लोरीन
Anti
फ्लोरीन
bonding,
गौच हाँ हाँ
Gauche
एंटी बॉन्डिंग
effect, Gauche
हाँ
effect,
गोच गोच इफेक्ट
not anti bonding, not
गोच
anti bonding. It is sigma to sigma star interaction.
ओके ओके सर
It is sigma to sigma star interaction. Okay, it is not anti bonding. I mean, the interaction is taking place from bonding orbital to anti bonding orbital, but the see, every stabilizing interaction is always bonding interaction, not anti bonding interaction. So what I said there is, it is the, so this is the thing. This is our fluorine, and so this is our fluorine. So here, sorry, I have to draw it in other way. This is our fluorine. In case of fluorine, we have this antibonding orbital, right? This is antibonding orbital. The interaction is not antibonding. This is antibonding orbital, CF sigma star, right? This is antibonding orbital, and here we have CH sigma. This is bonding orbital, right? Now this is filled with electron, and this sigma star orbital is empty. Sigma star orbital is empty, and this sigma orbital is filled with electron. So it can donate electron inside the sigma star orbital, right? So this is sigma to sigma star interaction. Is it clear?
यस सर यस
Okay. Okay. Thank you. I will stop the lecture here and see you in the next lecture.